Okay, YouTube, this is my first in a segment of videos in which we're going to explore kind of graphical analysis. And so this is kind of like one of my favorite things to do. It's like a science class. I give you a graph and we get to go read it, basically. But in this video, we're going to focus on what we mean by a graph increasing, decreasing, or being constant, as well as what we mean by relative and minimum and maximum values. Okay, so let's go ahead and start with this. We have the average fuel efficiency of new U.S. passenger cars, and I kind of like this graphic here. We can see that the year is our independent variable, and it looks like it's going by 5 since 1955, and then the average fuel efficiency. And so we can see that this graph here, I mean, if we just had to describe it, basically it starts off by decreasing from like 1955 to 1970. And then beyond 1970, good news is it starts to increase, and it looks like really dramatically increasing between 75 and 80. So good job on the technology there, guys. But basically, let's interpret a few things here. It says, during which years was the fuel efficiency decreasing? Well, you can see that this is the portion of the graph that is colored in blue. And so I'm going to write this here just in words. But we say between 1955 and looks like 1970. Okay, so the thing here is, when we look at this next question, during which years was the fuel efficiency increasing? Well, we know from 1970 all the way up to, it looks like our last data point here is 2009. It's increasing, but this time what I want to do is I want to kind of write this a different way. So notice when we're answering these questions, we're saying nothing about the miles per gallon, average miles per gallon. It's all about the input values. So if I want to say between 1970 and 2009, the way I'm going to write it is thusly, 1970 to 2009. And you'll notice that this time, instead of using this type of notation, which is just verbal, we're going to use what we call interval notation. And you'll also notice that I use parentheses on the endpoint. So on the open interval from 1970 to 2009. And the reason why is because, well, in 1970, what's it doing? You know, and it looks like we have like a minimum fuel efficiency here, the lowest it ever gets. So it went from decreasing to increasing, causing this minimum to occur. And I could say nothing about whether it was increasing or decreasing at that point. I just know that it turns around. So when we talk about increasing, decreasing, rule number one is we always talk about input values. We're using x values to describe this. And we always use open intervals. We'll never use closed brackets on increasing or decreasing. So we say, in which year is the fuel efficiency at a minimum? Well, it appears to be at 1970. If we want to talk about why, is because, well, our graph went from decreasing to increasing. And in which year was the fuel efficiency at a max? Well, at least on this closed interval from 1955 to 2009, I say closed because we do have the endpoint data here. I would say, 2009 looks like it's at a maximum here. So we say 2009. So again, when we talk about maxes and mins, we're talking about where they occur. When we refer to them, though, we use the x values. So what I'd like to do is very quickly, hopefully here, go over the definition of increasing, decreasing, and constant. But we talk about functions increasing. I want you to look at this first one here. This is our graphic of increasing. And you'll notice that we have some, what we call open interval I. So just some interval of x values. We say excluding the endpoints. These are clearly open dots here. But basically, given two x values, we're going to call this one x1 and this one x2, where x1 is to the left of x2 on this interval. If that's the case, then we say if f of x1, that is the y value at x1, if it is less than the value at the second x value there, the y value at the first x value is less than the y value at the second x value, then you must have been going uphill on this interval for all x1 that is left to x2 on this interval. So if f of x1 is less than f of x2, that is the y value at the first point is less than the y value at the second point, then you must have been going uphill. And likewise, we say that we have a decreasing graph if we're on this open interval I. Essentially, all x values to the left of this x value here, x1 to the left of x2, if the y value at the first x value to the left of that second x value is greater than the y value at the second x value that is to the right of the first x value here, then you must have been going downhill. So if f of x1 is greater than f of x2 for all x values x1 that are left of x2 on this interval I, then you must be decreasing. And then last but not least, we see constant. Constant basically implies that for all x1 to the left of x2 on this open interval I, if you were to plug in their y values here, how do they compare? And I would say, well, then f of x1 and f of x2, they're actually equal, and this would denote constancy. So really quickly, what I want to do is basically indicate what we mean also by increasing, decreasing, and constant. We would say the slope is positive if we are increasing, negative if we are decreasing, and the slope is specifically equal to zero slope if you are a constant graph. So really quickly, what I want to do here is state the intervals on which this function here, this x cubed minus 3x, is increasing, decreasing, or constant. This is actually really easy to do. It's just that lots of mistakes tend to be made in terms of reporting these intervals. So I'm going to write increasing, decreasing, and constant. We'll deal with this rather quickly. But I notice that it's increasing at first, and then it goes to decreasing, and then it goes to increasing again here. But when we talk about increasing, we're not going to say from way down at negative infinity all the way up to a height of around 2. We're not talking about y values. We're talking about x values. So where we have these really turnaround points right here, what we're going to say is that kind of splits our x-axis up. And we can see that we are increasing on our graph for all x values to the left of -1. So I would say on this interval right here, from negative infinity to -1, and not including -1, because I can't tell you really what it's doing at -1. It's actually a zero slope, but it's not increasing. So I can't say that it's increasing there. We use an open parenthesis. And then it goes to decreasing, and then it starts to increase just beyond 1 into infinity here. So when we have a disjointed set of sets here, we have to use a union of these two sets. So if we marry these two sets together, then we say on all those x values, we have a graph that's increasing. Whereas in the middle here, between -1 and 1 exclusive, we would say that our graph is actually decreasing. And I would say nowhere constant, so nowhere. Is it ever constant? Okay. So really quickly, when we talk about relative maxima and minima are just plural of maximum and minimum. And when we talk about maximum and minimum, we just say one or the other, okay? So we say these are the points of the function where it changes from increasing to decreasing behavior. We'll refer to these as relative max and min. So, you know, it makes relative sense here, no pun intended, that if we're going from decreasing to increasing, then what you get is a minimum value on your graph. And the only reason we say it's a relative minimum is because it's a minimum on some open interval I of values here. Compared to its neighbors, basically, it's a minimum. And then if we go from increasing to decreasing, we have some maximum. And that makes reasonable sense when you look at this. Really quickly, though, the formal definition says a function value f of a, so that's this one right here, is a relative maximum of f if there exists an open interval containing a. So if I had some interval of values here, I, and a is in this interval of values here, then we say if it's true that f of a, or the y value at that point, this y value right here, is greater than f of x for all x that are, first of all, not equal to a. So basically x is some other value on this interval, maybe right here, and it's not a, okay? Then for all x values on this interval, if we look at their y values, their f of x, the f of x values are all going to be less than this f of a value if and only if this is a relative maximum. And likewise, we have a relative minimum f of b if for all x values on this interval I, their y values, f of x, are greater than f of b, then f of b would be a minimum value, okay? So sometimes you'll see the word local instead of relative. So really quickly, just want to do this, talk about a couple of graphs that I have here, starting with this one here. This is some polynomial that I put in. And what I've done is, if I zoom out here, you can see that I've highlighted some points where it goes from decreasing to increasing, and then we go to decreasing and increasing. This point right here would be considered a relative minimum because it is a low point compared to its neighbors. And also, if I zoom in up here, this point 1.06 negative 3.03 is also a relative minimum. The only difference I want to point out here is this. These are both relative minima, but this would be considered the overall absolute minimum because it never goes lower than this point. At the same time, if we look, does it ever have an absolute maximum? Since this graph goes up forever and ever, it doesn't have an absolute maximum, but we recognize that it has a relative maximum just right here at 0, 0 because it goes from increasing to decreasing. Cheers.